All right, so here's the lesson for Introduction to Z-scores. So Z-scores measure the number of standard deviations an individual is from the mean. So in terms of how we calculate it, this is the Z-score formula. We have our data point, we subtract the mean and divide by the standard deviation. So that's going to tell us how many standard deviations we are from the mean. The symbols that you might see for mean may be mu, which is the Greek letter, but it also might be X bar. And the symbols for standard deviation you might see is that symbol right there, which is sigma, but you might also see S. In a later unit, we'll talk about the differences between those. Z-scores allows us to measure relative standing, where you stand in comparison to others. And it may be used to compare relative standing of individuals from different distributions. So for instance, you can compare males versus females. For instance, if you're talking average height, males and females have, males tend to be taller than females, so they have a different mean and standard deviations, but you can compare relative standing of individuals based off those distributions. Sometimes Z-scores are also called a standardized score. One thing to note, and we'll talk more about this in the next unit, that in order to use Z-scores, our data must be symmetric, and we'll talk more about why in the following lesson. All right, so let's take a look at an example. So it says the average 9-month-old male baby weighs 19.6 pounds with a standard deviation of 1.98 pounds. If Miss Okita's son Archer weighed 24.9 pounds at 9 months, what is his Z-score? So remember that the Z-score formula is X minus the mean divided by the standard deviation. So filling in what we know here, I see that it says the average 9-month-old weighs 19.6 pounds, so that's going to be my mean. It tells me that I have a standard deviation of 1.98 pounds, so that's going to be my standard deviation. And then it tells me that my data point is my son Archer, who weighs 24.9 pounds. So that's going to go here. So filling in everything in this formula to calculate our Z-score, it's going to be 24.9 minus the mean, which is 19.6, divided by the standard deviation. That's 1.98. So if we put that in our calculator, we basically get 2.676767 kind of repeating. Z-scores, we're always going to round to two numbers after the decimal. So since it says 676, so it says 2.676, and we want to round to two numbers after the decimal, meaning we want to cut off our number here. Since this number is a 6, we're going to round that to 2.68. So my Z-score is 2.68. So in terms of interpreting that in context, we would say that Archer's Z-score is 2.68. This means he is 2.68 standard deviations above the mean. If you were below the mean, you would have a negative Z-score. So because it's a positive Z-score, that means we're 2.68 standard deviations above the mean, so heavier than average. All right, so let's look at part 2. It says Miss Okita's friend has a 9-month-old baby girl, and she weighs 23.1 pounds. If a 9-month-old baby girls have a mean weight of 18.1 with a standard deviation of 1.98 pounds, who weighs more relative to their distribution? So boys tend to be heavier than girls. So again, we're going to work with the Z-score formula, which is X minus mu divided by our standard deviation. So filling in what we know, our mean weight is 18.1 pounds. Our standard deviation is going to be 1.98 pounds, so same as the previous distribution. And then our data point, we're looking at the weight of this baby girl, so that's going to be 23.1. So figuring out my Z-score, it's going to be 23.1 minus 18.1 divided by my standard deviation, 1.98. All right, so this has a Z-score of, it's 2.5252 repeating, so we're going to say 2.53. So the question isn't what this baby girl's z-score is, it's who weighs more relative to their distribution. So remember in the previous example, the z-score for Archer was 2.68, which means he was 2.68 standard deviations above the mean. This baby girl is 2.53 standard deviations above the mean. So in that case, we're just comparing who is further from the mean. In that case, it's Archer. So I'm going to say Archer is weighs more relative to his distribution. So what we're using to actually answer this is not the actual weights of the individuals, but the z-scores. Because even though we can see clearly that Archer obviously weighs more, we're not comparing that with a baby girl. We're kind of comparing it to how far away they are from the average. All right, so if we think about these questions, and it says, suppose that instead of giving your score on a test, I wrote your z-score. What type of z-score would you want to see? So if we're talking test scores, a z-score that we would want to see is probably a positive z-score, because that means we were above average. So positive z-score would mean that we were above average, a negative z-score would mean that we were below average, a z-score of 0 would mean that we were equal to the average, since the z-score formula, remind you, is x minus the mean over the standard deviation. So we know that if this were to equal 0, that means this would have to equal 0, which means that your data point and your mean would be equal. All right, so let's take a look at a couple more examples. So it says Nicole's score on the stats midterm was 80 points. The class average was 72, and the standard deviation was 5 points. What was her z-score? So using our z-score formula, our data value is going to be 80. Our average is 72 divided by our standard deviation, which was 5. So this is equal to 1.6. So I'm going to say Nicole's z-score is 1.6. She is 1.6 standard deviations above the mean, which means she did better than average. All right, looking at the second one, it says the town's January high temperature average was 36 degrees with standard deviation of 10. While in July, the mean high is 74 degrees with a standard deviation of 8. In which month is it more unusual to have a day with high temp of 55 degrees? Okay, so let's first calculate the z-score for January. So for January, this is our data point. It's going to be 55. The average temperature in January is 36, and the standard deviation is 10. So this is a z-score of 1.9. So now I'm going to calculate the z-score for July. So again, our data point is going to be 55 degrees. The average temperature in July is 74, and the standard deviation is 8. So this gives me negative 2.375, which we're going to round to negative 2.38. So to determine which is more unusual, we want to see which one is further from the mean. So in that case, negative 2.39 is further from the mean. It is negative 2, so about 2.39 standard deviations below the mean. So I'm going to say this is more unusual. In July, because it is 2.39 standard deviations below the mean versus in January, it's only 1.9 standard deviations above the mean. All right, so we can also use z-scores to kind of work backwards. So this example says the average score on a stats midterm was 75 points with a standard deviation of 5 points. And it says if Gregory's z-score is negative 2, how many points did he score? So remember the z-score formula is z equals x minus the mean divided by the standard deviation. So in this particular problem, the information we have is a little different. We have the z-score, which is going to be -2. We have the mean, which is 75. And we have the standard deviation, which is 5. In this particular problem, we are solving for our data value, our data point, which is x. So we're going to fill in everything we know. It's going to be -2 equals x minus 75 divided by 5. So first, I'm going to multiply both sides by 5. That's going to get rid of the 5 in the denominator. So -2 times 5 is going to be -10. So I have -10 equals x minus 75. And to finish solving for x, we're going to add 75 to both sides. So -10 plus 75 is 65. That's going to be our data point. So I'm going to say Greg got a 65 on the stats midterm. Which, if we knew the definition of a z-score, we should be able to do that without maybe doing all of this algebra, right? The z-score of -2 is 2 standard deviations below the mean. If 1 standard deviation is 5, 2 standard deviations would be 10. So 75 minus 10 would give us a 65. All right, last question here. It says a highly selective university will only admit students who place at least 2 z-scores above the mean. So that means z is going to be +2. It says on the ACT has a mean of 18 and standard deviation of 6. We want to know what score an applicant must obtain to be admitted to the university. So using the same formula as before, we have the z-score, which is 2. We're finding the data value. That's the minimum score we need. The mean is 18, so -18 divided by 6. So using the algebra, we're going to multiply both sides by 6. So 2 times 6 is 12. So that's how many points is 2 standard deviations. And then we have x minus 18. And then lastly, we're going to add 18 to both sides. So that's 30. So the minimum score to be admitted to the university is 30. So again, we can kind of do like that the way that we did the previous one. Since it gives us a nice round number for a z-score of 2 standard deviations above the mean. Well, if it's 1 standard deviation is 6, 2 of them would be 12. And since we're above the mean, we would just be adding that to the 18, which is what we did here, right? 18 plus 12, that gives us 30.